Hello there, this is Brent with Johnson Fabrication and Controls. Today I'm wanted to talk about something a little bit different, a little off topic, slightly out of cue, mainly talking about microcontrollers. For this video, not specifically Atmel, but generally some Arduino products, some Atmel products, the 328P, the 328 surface mount, and along with the DIP series. Both which I have used not only for prototypes but for actual products. Specifically, there's some issues with inductive loads, not just for this style Nano, they would call it. This is a development board called a Nano, and here you have an Uno, but for both, they both have issues, and along with some other Atmel products. I have not personally tried the other ones, but the 328P I have tried with numerous issues, mainly regarding inductive loads, interference. To kind of go over a general idea of what's been going on, I have had at least 2 or 3 controllers designed around the 328P, which do work, but do require external snubbering, either a snubber diode, a flyback diode, a free will diode. There's lots of clamping devices that you could put across whatever your load device is, typically a DC solenoid or a DC motor. In my case, I typically use DC solenoids, fairly low wattage, typically in the range between 2.3 watts all the way up to 10 watts, so it's fairly low. No crazy current draw. Excuse me. I do occasionally use some AC devices like AC solenoids. So with using AC as external devices or load devices that are inductive, they tend to be a little more problematic. You have to end up using capacitors, resistors, and MOVs, varistors, to basically try to absorb not just transient back voltages, but there is a phenomenon described as back EMF that all these devices basically produce when they're energized and they're de-energized. So overall, there's an entire phenomena here that's been going on, not just with Atmel, like I previously mentioned. There is a lot of microcontrollers. I've come across a lot of microcontrollers over the years. I've been finagling and installing electronics, control systems, specifically for animatronics and other professional gameplay applications and amusement park applications. For over the last 20 years, I've come across quite a few controllers, and honestly, all of them have the same problem. The only ones that do not are industrial grade equipment, such as programmable logic controllers, brands like Allen Bradley, Koyo, Siemens. There's a lot of industrial grade PLCs that primarily do not have these issues unless they're completely bombarded with EMF, like massive installations that have huge compressors, like 10 horsepower compressors starting up. And even then, typically those devices do not even have issues in those environments. So the problem is really the entertainment industry. Most designers / installers / animatronic builders tend to go with microcontrollers that are very easy to program, and typically generally have a lot of issues down the line after being installed and or working on a long-term condition or a long-term environment. So I just wanted to bring up I can throw out a handful of microcontrollers that I've used that I know do have issues long-term. One that I used for nearly 10 years was Gilderfluke Robotics. They have great features, great software. The original Mini Brick 8 I started with, way back in the day when it still had real components. There wasn't all this tiny stuff on board and tiny little cases, tiny little buttons. This is way before they introduced the buttons on the controller. It was the PC Mac software. It was a great controller, very easy to program. You program it in a linear fashion. I began blowing out driver chips. I believe they use, I don't know the exact type of driver, but most of them are a ULN 2803. I blew numerous drivers, smoked them, literally ejected material. Stuff would literally blow up, and I never really understood why. They just kept sending me replacement drivers. So it wasn't until later I began to notice that you really did need a diode, which is right here, across your load device. And for my application, that load was an inductive coil, energizing a pneumatic valve. So aside from Gilderfluke, many other companies like FX Tech, they sell the Parallax line of Prop 1 controllers. They sell some easy Prop 8 controllers you can program with buttons. Those had the same issue, the exact same drivers. Drivers would fail. You'd get transients across your I/O pins, your inputs there was no debounce. So even when there was a debounce programmed, things would just turn on randomly. Things would turn off, things would freeze up. Most of the time, channels would blow out. So you'd install your controller, say a month later, you'd get a call saying, hey, this channel stopped working. And typically what happens is you're cycling a valve on and off at a certain rate. Sometimes when it's pressurized, the valve can draw a lot of current. Sometimes it can fluctuate in how much current it draws. So your back EMF and your transient that's being produced on that pin, if you're driving it directly from a driver, it's going to fluctuate a lot, and you're going to get massive varying results. In some applications, if you have a 12-volt solenoid, this solenoid can not only produce twice the amount of current draw, it can create basically an artificial voltage. It's a real voltage, but it's because of the increasing current in the coil, and it can be in the hundreds, sometimes thousands of volts, even momentarily, and it would basically blow up anything. I've seen it happen. It's happened to me hundreds of times. It's crazy. It's a really bizarre phenomena. So not just with the Gilderfluke and the Prop 1 controllers, the Parallax controllers, the Peekaboo controllers. There's a whole line of Fright Ideas controllers that literally it's like the latest craze everywhere. It's probably the most popular line of controllers used out there today. Internally, they use a PIC controller. I have personally had the same problems with most of their controllers. Same thing, blowing outputs, channels locking up, memory erasing itself, audio latch up, processor latch up. Same issue. I'm not trying to rag on one company or another. I'm not here to pick even on Atmel. This is a general thing that's been happening for decades, and no one really seems to talk about what is actually going on. Why are people so using these controllers in applications where we can't control the load device themselves and protect them properly? But because honestly, whether it's a customer installing the product or a customer buying a finished product, I have honestly never seen anyone put a diode across a coil in an animatronic that I've seen in person. I've seen hundreds, if not thousands, of animatronics, and I've personally built hundreds and thousands of animatronics, and I have never personally seen anyone put a diode across a DC coil, or even let alone a DC relay coil, even though you're supposed to do both to protect an output device or an output pin, or an output pin from a driver. So what's happening is basically most people buy it, assume that it's ready to go, and most of these controllers are absolutely not ready to go. So it's the furthest thing from it. You need to do a lot of extra work putting diodes, basically anti-parallel across the coil contacts, of a relay. And if you're using that relay to switch a load, you would need to protect those load conductors. So if you're using a common or a normally open or a normally closed to cycle a valve, AC or DC, in an AC application, you would attempt to use, it's called an RC snubber. You'd basically use a series resistor linked to a pin of a capacitor, and you could do that basically in parallel with your actual circuit. So you could go across your load conductors, or you could go in parallel with it to try to absorb basically that back EMF event and absorb some of the excess current and transient voltages that are produced there. Now, specifically with the Atmel products, the 328P, the most common what I've done here is, like I said, I've had two products designed that do work. Unfortunately, I'm stuck with basically using DC load valves, and I use fairly big diodes. I usually use 600 volt 6 amp or 1000 volt 6 amp. Sometimes I'll drop it down to a 3 amp, but I usually keep it very beefy because I know that DC solenoids produce very, very large transients. Very large. I mean, sometimes I even shock myself seeing some of these voltages. So usually with DC load applications, if you're using the diode and you're putting a valve, you want to put this across your two leads, and you can see the forward bias. You have an indicator on a diode, usually the gray strip or some type of line. That's your forward bias. So voltage usually flows this direction. In this case, you want to put it so that way, usually the strip will align with your positive lead, which is usually indicated as a red or black wire. And that usually does the trick for DC coils, for DC valves. Sometimes you'll notice that a diode can fail in the field because it does reduce basically the switching action of the solenoid itself. It does degrade over time. It's not a perfect solution, but it's the most typical you see in industrial environments too. They install these actually in the coil. So that's the most common for DC. AC, like I said, you can use the RC snubber. You can even use an MOV along the leads as well. So you can do it either in parallel or in series. You can go across the coil of an AC, or you can go in parallel with the circuit. I typically like to use MOVs as well. The problem with trying to protect AC devices is that the efficiency using an RC, basically using a resistor and a capacitor, and even an MOV across an AC coil, is what you'll notice is it depends on your switching frequency, meaning how fast you're turning on an output, how long of time you're allowing it to basically not be active. So the on time and the off time will be your on frequency, basically how frequently you're switching that output on and off. And what you will notice is that the average will be about 40%, 40 to 60% and I've done a lot of tests with AC valves and DC valves. The good thing about an RC snubber is that you can use it for both AC and DC coils. So originally what I tried to do was create a new layout for a controller. And basically what's going on here is, it's fairly in-depth. Let me go back to the original picture here. So what most common relay boards have nowadays is something called an optocoupler or an optoisolator. There's a lot of different brands. Typically you have two pins in, so you have an anode, a positive lead and negative lead, and then on the other side, typically most applications are syncing the same ground to another device, like let's say a transistor, or that transistor can drive a relay. And that's typically driven by a low current output, say something like 20 to 40 milliamps from a small microcontroller like the Atmel 328P. So in our latest designs, we utilized optocouplers not only for inputs, but for outputs. And these optocouplers were driving transistors, which drive larger relays, like say a 5 or a 10 amp relay, to drive a larger load, a larger inductive load, like a solenoid valve or like a motor, AC or DC. So obviously there's inherent isolation within the relay because there's mechanical separation in the actual switching action. Unfortunately, you do get contact bounce, you do get some arcing across contacts with a mechanical relay. And you can use SSRs. Unfortunately, what you'll notice is that most SSRs are not rated for inductive loads, only triacs are. You'll find that 110 volt, or AC, I should say, sinusoidal triacs that allow AC switching do come with snubbering on board, and unfortunately even those efficiency rates are very low. So you'll hear a lot of cases where people say just use an SSR there. Unfortunately, you'll notice that you can blow up a MOSFET very, very quickly driving a solenoid valve. So really what it comes down to is that most of these controllers are not ideal for driving inductive loads. And the problem is, let's say you wanted to take this opto to drive a transistor, to drive a relay. People will say, well, just install an external relay. The problem is that even through trials and testing myself, using an opto-isolated output to drive a relay, to drive another relay, to drive this valve, you will notice that transient will still return back to this processor. Even if that secondary relay is, say, 10, 20, 30 feet away. I've seen it happen. It's almost a mystery. And you begin scratching your head, what is happening? And I really honestly don't know the full... I can give you general words that people use to describe the EMF event, the back EMF event. And most people will tell you just put a protective suppressive device, whether it's a freewheel diode or a snubber diode or an RC circuit, across the load device. And that does work. Like I mentioned, the efficiency degrades. But what my question is, what's wrong with these line of microcontrollers? Why are they so sensitive that they just keep shutting down? Basically what happens with most of the Arduino products is that when you try to switch even a local load, I can switch this relay, no problem. The minute I try to switch 12 volts across it and it's inductive, oh, this thing immediately shuts down. It's like terror on wheels. This thing can barely hang on for dear life. It resets, it sets, it resets. It begins oscillating at weird frequencies. And you'll get the same behavior, whether it's a Nano or an Uno or even some of the larger Atmel processors. It's very, very frustrating. You cannot get consistent results. You'll notice that programs hang up, memory erases itself. And some of the memory or the EEPROM issues may not be related to inductive loads in general, but it sure doesn't help. So overall, that's a general concern for most of these products. But my comparison is, if a PLC can do it, it has zero issues. Like I said, there's probably 99% of the time you will have no issues. I typically use Koyo PLCs, and I can't think of a single time I have ever seen a PLC just reset itself or just shut down or turn off. It doesn't happen because they're very reliable. They're meant to work consistently, basically 100% of the time. I mean, nothing's perfect, but these PLCs are very, very robust. And I've looked at a few of them myself internally to kind of get a glimpse inside of what's going on. And outside of basically utilizing some octal buffers, they use, coming out of the I/O pins, they use something called an octal buffer. And it basically takes the signal of an output and it's regenerated through the chip. So it's not driving the load directly. But outside of that, it's hard to explain how they're able to clamp all these excess voltages. And that's what we're trying to do, is clamp down the excess voltage from these devices so they don't come back and hitting your transistors, hitting your relay coils, and basically multiplying current. And that current, it gets generated into even higher voltage and comes back. But another issue that becomes mysterious for designers and builders is most of these devices have pretty high ratings on them. Unfortunately, these voltages manage to sneak through, even if they're not coming through the actual component, they somehow manage to sneak through the magnetic field surrounding the device, whether it's a controller or a conductor coming out from the controller. They seem to sweep across these conductors, and these things just shut down. I mean, it's the most frustrating thing when you're troubleshooting something. You're just like, and it's never consistent. A channel might lock up in the on position. It might shut down completely. It might be mid code and it's running some loop, and you'll notice that it just starts flashing. All these entertainment little microcontrollers tend to have the same behavior the minute you want to turn on a real device. So my point is, it's very hard to actually use these type of controllers in the field, because why would you be using a controller if you want a flashing LED? I would probably say you're probably going to be okay, still maybe protect this device, but that's a little crazy just to turn on an LED. But most applications, you need to turn on some type of load, turn on a device, charge something, turn on a motor, do something with it basically. And these honestly don't really seem to handle very much other than running code. And even the code has issues because the memory, or how it's programmed, depending on what registers you're using and what timers you're using, or how are you using the processor to evaluate your code and how that's interpreted internally. It has even a harder time doing that, let alone actually using the I/O. So part of this is not really trying to tell you how to design something right. With these controllers, there's a huge gray area for me. My mind is literally half full, half blank with these controllers, because the longer that I scratch at these, I begin to realize I honestly don't know what's happening, why these things are so sensitive. And in my normal train of logic, I would say these are absolute junk. I wouldn't waste my time with these things. There's a lot of really good controllers that are more mid-range. STM makes some pretty decent controllers. I've done some personal testing with, and honestly, they behave a lot more consistently than these. I haven't had any issues with the STM products, and I've done some really heavy bombarding, not just with inductive loads, but with both AC and DC inductive loads and some motors as well. And I've let to actually have one reset or even shut down on me, lock up. I haven't had the issue. There might be some cases online where you read of installations where they're driving a motor, they're using it as a motor controller, and whether it's pulse width modulation, it seems that some of the STM products have problems with pulse width modulation for outputs driving certain inductive loads. But it's hard to really know, but I typically don't post about this type of design process. If something doesn't work, I basically throw it in the dumpster, or if it's a real piece of equipment, I'll rip it out and I'll put a PLC in because I'm tired of hearing about it. But basically, here is my design, my latest design. It was going to be called the ISO series, the isolated series, 1 channel, 2 channel, 3 channel. And as you can see, what I did build a prototype for, based off the 328P, was the processor driving an octal isolator, driving a transistor. The transistor then drives an onboard PCB relay, being 5-volt coil. And from there, you have your normally closed, normally open contacts. You can switch DC, AC. But what you'll notice here is that this little line coming across this page represents total isolation. What I was doing differently, most of my previous examples of microcontrollers that were actually built were utilizing the same power supply inside on the board. And a lot of that is counterintuitive. You don't necessarily want to share a ground. If you're switching a ground here and you have an anode and a cathode, so whether you're sourcing voltage from your processor, you don't always want to share a ground because you might get noise that's induced just on the actual board layout itself, especially if you have coils, if you're switching any coils or any just noise at all, if you're running audio equipment. So what I did was this line represents a secondary power supply, a primary power supply input for the MCU itself, a secondary power supply to basically drive all the switching equipment on the back end, being 5 volts, and then another power supply that can actually be linked to drive your actual inductive loads, your actual switching, your actual load equipment. So, it was going to have different connectors, some M8 connectors, and it was going to basically allow you not to have to wire these terminals. You could basically plug in your power supply, have an M8 connector come in and go to a typical solenoid valve connector or another device, and it would be very clean. You wouldn't have wires coming across the join commons, and you wouldn't have wires coming here. Nothing would be visible, but would very nice, and it would only come to the connector and like very visibly attractive and be very clean, very professional. The problem was that once I actually built this prototype, it didn't work. I had the same problem that I did with the previous versions of controllers, that regardless of keeping this ground separate, this MCU, being either the Nano or the Uno, reset. And what I started doing was I took the load contacts in parallel. I installed an MOV along with a series resistor and capacitor. And that's just basically the supply lines coming to the valve. So along the hot, you can imagine like a neutral and a hot on an AC line. Along the hot line, along the hot conductor, I installed an MOV from neutral to hot. I installed a series resistor and a series capacitor along the hot conductor. And it did work. It only helped about 40%, but I could never drive the solenoid any quicker than, say, 2 seconds in between. Any pulses that were quicker than that, any cycles that were closer together, it would immediately lock this controller up. And remember, this load is not being driven from this processor. This processor is driving an opto isolator, driving a relay, an opto isolator driving a transistor, driving a relay, and I had numerous protection. I had a 2,000 volt diode coming from not just the collector part of this transistor, 2,000 volt, and that's for DC and AC signals, sinusoidal waves and direct current square waves. So, and then I have a snubber diode coming across the not just the coil of the relay. I installed protection directional diodes coming to the actual isolator, then across the anode and the cathode of the isolator. Then I installed, like I said, I installed a 12 volt DC, or actually 18 volt DC MOV across the coil of the relay. I was trying to reduce the amount of noise and current coming through this relay. So I wasn't getting the back EMF. Nothing worked. Absolutely nothing worked. The only results I had was using the RC Snubber, and I was able to run about 4,000 to 8,000 cycles on this prototype. But the minute I wanted to change the load device, like the valve, or I wanted to change the cycle rate, the whole thing fell apart. You could not get this controller to stop resetting. And honestly, it was the craziest. If you were to look at the circuit, it's a little insane. At this point, I was coming up with an idea to drive a solid state relay from the octal isolator to drive the transistor, which is going to, and then drive a different type of mechanical switching device so that I can use AC and DC. And I don't have to use a mechanical relay. The problem is that it's not going to fix the issue of having a controller ready to go that has a variable load output. So meaning someone can put AC or DC here, wire it up, and not have to install this diode across there, because no one does it anyways. The problem is that when they don't do it and they start using it, they say, well, this thing's junk. This is trash. Why do I have to put a diode here? And there are a lot of microcontrollers where you do not have to put anything there. Like I mentioned, the problem is with those entertainment controllers is that 6 months later, this thing stops working. The whole thing stops working. Your audio goes out, channels blow out. So but what you want to do is compare it to a PLC. PLCs don't have these issues. So I want to wrap it up basically by saying that this is what I've experienced with Atmel products. Let me go back to this picture. So I would say be very cautious when spending a lot of time designing, trying to figure out what's wrong with the actual microcontroller, unless an engineer wants to hop on here and actually dump some real data of what I think these things are basically crap. I think they're basically too sensitive to be used in any real environment. A lot of those data sheets are either wrong or they're hard to interpret because a lot of the max volts ratings or the automotive classification for Atmel is very misinterpreted. They might say automotive to turn on an LED inside your car, not to actually be susceptible to receiving any type of inductive noise or interference. But you need an engineer to really look at it and basically take real experience and say, oh, I've used these before, these are junk, or you got to use them exactly like this. I mean, if you have to spend $2,000 in parts to protect this small IC, perhaps it's not worth it. And that's where I've come down and realizing that there's other processors and industrial devices that are way better than this junk, way better than this trash. Not to say that they're not good. There's a lot of really good features with Atmel. Especially with serial communication, RS-45. There's a lot of really good features, but why in the world would you spend years and years trying to figure out what's going wrong with something that's so cheap? That's exactly what it is. It's cheap junk. Anyways, I want to wrap it up, and I usually try to stay on a positive note. I just wanted to throw all this out here in case someone comes across this video and has the same issues with inductive loads. And if you want to ever message me or want me to share a little more in depth what some of the experiments that I've done, like I said, my conclusions were basically they're good for only DC loads when you can protect the actual load device, either with a diode or some type of RC snubber. Keep the cycling rate way down, and you got to use optical isolators. You got to really protect this MCU because this thing is basically like hell on wheels. It's ready to go out at any moment. But if you can try to stabilize it a little bit, it's going to run somewhat consistently. It's not going to be anything reliable. I wouldn't put my kid in it, and I wouldn't even put groceries down the street with it. But if it works, then great. Anyways, if you want to reach out to me, I hope you have a wonderful day, and thanks for joining in. Okay, bye.